In a previous video, we've looked at how the equation force equals mass times acceleration can be used to calculate equations regarding connected particles, so two things that are moving but are held together by some light, inextensible string or rod or tether or so forth. In that video, I mentioned pulleys, which are this other example of connected particles, which may now just want to be considered in their own right. When looking at pulleys, again, we're going to have two things that are connected together by some kind of string. However, that string passes over a turnable circle, a pulley, either in a way that has both of the particles suspended in the air hanging downwards, or that has one of them on a surface and the other is going to be hanging downwards. In the examples of those which are hanging, the forces that they're going to be subject to are going to be their weights. And while this other one here does obviously have a weight, because it cannot go through the table, we are not going to be considering it here as a relevant force. When you get into A2 and are looking at friction, it will actually start to have an effect, but we'll be focusing on the idea of friction specifically in the video that also talks about slopes. So for now, we're just going to look at it when we're suspended in the air. As well as this though, we're also going to have some resistive forces, which we're going to find in the string itself. We can refer to this as tension when the two blocks are trying to pull away from each other, and thrust when they're pushing into each other. In these cases though, with the pulleys, they're always going to be pulling away. They should always be. So when we start to construct our F equals ma equations, we're just going to work out, first of all, in which direction is the individual thing travelling, and therefore what is the driving force and what is the pulling force. In the example of this here, where they're both hanging in the air, one of them must move down and one of them must move up. So let's just say the left-hand one is moving down. If it's moving down and the string is inextensible, it can't stretch, therefore this other one must be pulling up. Whereas here, we're going to assume in these scenarios, the question is going to tell you that the one that's hanging is heavier, so it's going to be moving down, and meanwhile, therefore, the one on top is going to be moving to the right towards the pulley. Now, the situations can change. Potentially, the one that is descending is going to hit the floor, in which case all tension is going to disappear from the string. It's no longer going to be stretched tight. And once tension disappears, just as how in any mechanics question, as soon as the situation changes, you want to redo your model, draw out the diagram again, or redo the equations, the equation of motion for the remaining thing is going to change now, because it's not going to have a forward force anymore. It's just going to be accelerating downwards under its own weight. And of course, we're going to get to examples of that when we go through the actual questions. Alternatively, it may not be that the descending thing reaches the ground, but part of it breaks off in some way, or something happens that means its mass now suddenly becomes less than the mass of the other thing. This means that the particle that was ascending, that was rising up, is now the heavier thing, so it will now want to be what's accelerating downwards. That being said, it can't just suddenly switch from going up to going down. It'll have to decelerate to a velocity of 0 first of all, and then start to drop. So, whenever you have this kind of question about, well, what's the greatest height that the ascending particle reaches, whether it's because the other particle hit the ground or because something else changed, you're looking for when v equals 0 after that ascending particle starts to only under their own gravity, or indeed just under that altered tension. And now that you have this introduction of velocity, we're also going to have a distance that it is rising, a displacement. Again, that acceleration, which is constant within the given section of the scenario. We can now bring in our Suvat equations, which, just if you need reminding, are going to be v equals u plus at, v squared equals u squared plus 2as, s equals a half u plus v times t, s equals ut plus half AT squared, which of course then has that variant of S equals VT minus a half AT squared, just in case you don't have that U. Some other things we may then also just want to be sure we can work out is the idea of impulse. So for an impulse, we're saying that that is the mass times the change in the velocity. You could see it's the change in momentum if we're doing physics. But yeah, so on impact, so when the descending particle hits the floor, it is going to experience an impulse, its mass times by, if it's come to a halt, come to a stop, then it will be 0 minus whatever velocity it had just before hitting the ground. Or if it was to bounce back up, which I doubt would be the case in this scenario, but if so, that would then be your v, whatever velocity it bounced back up with. Then is also just the idea that we can work out what force is exerted on the pulley itself. If we were to give the example of one, such as what's just on the left here, we have one horizontal rope and then one vertical rope on the other side. Tension technically is acting in both directions everywhere throughout the rope. We just think of it as acting right on the top here because that's the way the box then moves. And you think of it as acting up here because that's the resistive force against the weight. But we're also going to have tension pulling to the left against the pulley and pulling down against the pulley. This then results in a resultant force that would be splitting it down the middle in this case. Because we can think of this as just a regular right angle corner, this would now be at 45 degrees. It's only 45 degrees if it's a corner like this. But then what you could do is make these into right angle triangles. You want your tension to be the hypotenuse of this right angle triangle here, because it is the resultant of that force, is the overall actual force. These other sides here would just be components of them. So this resultant going down the middle here, that is going to be the sum of the two adjacent sides of these two triangles, which are going to be identical triangles because they both have a hypotenuse of t and they both have an angle of 45. T, presumably you'd know by this point, but we'll just say it says 2t cos 45 because you would do the hypotenuse times cos, leaves you with the adjacent. Again, of course, we are going to talk about that in an actual example later on, but it's a concept you may just want to be aware of already. To get into the actual examples then, just to experience what does it mean to be applying these concepts in what context. We'd have here, so this example of a pulley on the top with two particles then hanging down from it, so particle A and particle B, where A has a mass of 2m, we don't know what m is, and B has a mass of 3m. So the system is released from rest with the string taut, so that means that there's tension in the string. After descending 1.5 meters, B strikes the plane on the bottom, so the floor, and is immediately brought to rest. Show that the tension is 12/5 mass times gravity. Find the distance travelled by A between B striking the ground, striking the plane, and the string becoming taut again. And then given that m equals 0.5 kilograms, find the impulse of B striking the plane. Okay, well, to start off with, if we're going to be working out what the tension in the string is, we're going to need some F equals ma expressions for both A and B. For A, because it is the lighter of the two masses, it's going to be travelling upwards. So we're just labelling a diagram here with our T's, and then you have downwards here a weight of 2mg and 3mg, because weight is found by mass times gravity. Because it's moving upwards, its forward force is the tension. Then we'll take away that resistive force of the weight of 2mg, and that resultant here will equal that mass times acceleration. So the mass of 2m times by some other a that we don't know. And for B, we can say that because it's moving down, because it's heavier, the 3mg is its forward force, with T now being the resistance, and that gives you 3ma. Well, if we were to rearrange the top expression here, you can get that T equals 2ma plus 2mg, and so you can then substitute that into B's expression to get 3mg minus 2ma minus 2mg, because they're all becoming, or both becoming minus, because it's minus the whole t, and that will equal 3ma. Well, then just bringing the like terms together, 3mg minus 2mg is just going to be a single mg, and then we'll add the 2ma over to end up with 5ma here. From this point, we can cancel the m's because they're present on both sides. In fact, we actually could have done that in the previous step as well if we had spotted it. And then to get acceleration on its own, you just divide by the 5 to get the acceleration at the beginning is g over 5, a fifth of gravity. The question isn't asking explicitly for the acceleration though, we need the tension, so we'll now plug that back into here. So we'll say the tension equals 2 times the mass times a fifth of gravity, and then that plus 2mg. Here, what we can say is, so 2/5 of g add 2g. Well, that's going to be the same as 12 over 5 mg here if we collect the mg's together and then bring together those coefficients of the 2/5 and the 2, which, because it's a show that, we now know is going to be correct. And as we can see here, actually, if we don't know what the m is at the beginning, we don't have to worry too much about it. Your answer may be fine just to leave it in terms of that m. Secondly then, now that we know that this is a tension, we can start trying to work out what the distance is going to be travelled by A between B striking the ground and string becoming taut again. So because we're going to be looking at distances, we're going to be dealing with suvats. For this, we are first of all actually going to need a separate suvat to work out how fast A is moving when B strikes the ground. So we'll say if you've got your S, U, V, A, T, we know from what we just worked out before that the acceleration is going to be a fifth of gravity. We're looking at U being 0 because they were released from rest, V we're trying to find, and S here is the 1.5 meters that A rose. So we don't have T, we don't have to worry about it. What we can say is that using the v squared equals u squared plus 2as identity, v is going to end up being the square root, well, it would be u squared, but 0 squared is still just nothing. So the square root of 2 times your a, which is a fifth of gravity, times by your s, which is 1.5. So altogether, you end up with v being the square root of 3/5 of gravity, or 0.6 gravity, if you prefer. You could also substitute in 9.8 for the g at this stage, it's up to you. But either way, now that we know how fast A was moving when B struck the ground, that is now going to be our u for the new scenario when there is no longer any tension in the string. So yeah, because the scenario has changed, we have to create a brand new suvat. We can't assume that anything is carried over other than this v becoming the u because of how we've set it up. So the u is going to be that 3/5 of g. Because we're looking for the distance travelled by A between it striking the ground and becoming taut again, what's going to happen is A has already made it to some point up here. However, it's then going to rise a little bit further and then come back down. Because at this stage B is touching the floor and presumably isn't going to rise up again, when A comes back down and becomes taut, that's going to be A returning to this position here. So we're going to have it go up to its greatest height, then come back down again. So either we can set the displacement as 0, because if it's returning to the same spot, the displacement will be 0, or you can look for the greatest height and then double that distance. I'm going to suggest we go with the greatest height, just because we have more certainties when it comes to that. There's more figures that we already know. So if we try to find the greatest height, there's going to be a distance that's our unknown s. The v will be 0 at the greatest height, because again it has to come to a halt before it can come back down again. Now that there isn't any tension, so B has struck the ground and tension disappeared, A is now only accelerating under gravity, but specifically it's going to be minus g, or minus 9.8. You could make either the u or the a the negative, just one of them. There needs to be some indication mathematically that the speed and the acceleration are in opposite directions. You are moving upwards still, but accelerating downwards. And then once again, that just means that we don't have a t. So we're once again going to employ the same Suvat equation, but we're going to have to rearrange it slightly differently here. So we're going to have to say that s is going to be v squared minus u squared over 2a, which in this case is going to be 0 minus, and this squared is just going to get rid of the square root, so it's going to be over 3/5 g over 2 times the minus g. What ends up happening here is that the g's are going to cancel the minuses, leaving you with just 3/5 divided by a further 2 to leave you with 3/10, or just 0.3 meters. As I said though, this is just the distance to the greatest height. It will become taut again when it's now fallen back to that previous position, so we double that distance. So overall, the distance is going to equal 0.6 meters for that answer to the second. As for the impulse, because we're now looking at B striking the plane, we're going to be having its mass times its change in velocity. For the mass, we know from above that it could be expressed by 3m, but now in the question, we have that m has a value of 0.5. So, when looking at B, the m is going to equal 3 times 0.5, which will give us 1.5 kilograms. The u is going to be the v from A while it was ascending before B hit the ground. Because A and B are going to be accelerating at the same rate from rest, just in opposite directions, if A was moving upwards with the square root of 3/5 g, then B would have been moving downwards with the square root of 3/5 g at that moment. But then as for its v, this is going to be 0, because then the B is striking the ground, and we're told that it's immediately brought to rest. That as well, just confirming it for us. So you're going to have 1.5 times by 0 minus the root of 3/5 g for that m times v minus u, and that gets you an impulse of, and it's up to you whether or not you acknowledge the minus, because overall it's just an expression of a force over time, of 3.64, and the units would be Newton second. Alright, if we're okay with that, and we're happy with how we're taking a pulley situation, constructing both F equals ma and Suvat equations for those connected particles, allowing us to work out accelerations, velocities, distances and all that, even if the scenario changes, meaning that we have to recreate our models to make sure we're not incorrectly carrying anything over. If we're all good with that, let's just see how we could get along with an example of our own. Now, what if you were to have this question here, where you again have pulleys with objects connected on either side. However, here, this A is a single block of mass 3m. And on the right-hand side, we have both B and C connected together, each individually providing a mass of 2m. Now, the system is released from rest. When A is then 0.7 meters above its starting position, C separates from B and falls away. Find the initial acceleration and tension, then the speed of A when it is 0.7 meters above its starting position, the acceleration of A after C separates, and then the greatest height that A reaches above its starting position. So, consider what the different F equals ma expressions for each of the sections are going to be at the beginning and then after the model changes, how we might be able to work out T's and A's, and then what information you need to construct Suvats, which directions things are going in, and so forth. Maybe look back on the example we just did. Either way, pause the video, just have a go for yourself, and then press play again when you're ready to compare. Alright, So if first of all we're going to be finding the acceleration and the tension of these initially, so before the situation changed, we're going to work out where the forces are. So as always, we're going to have some weights coming downwards. So the weight of A is going to be 3 mg, and then the weight here combined will be 4 mg. Then you have your tensions going upwards as so, with them being the same tension as each other. Because B and C together are heavier, they have a greater weight, so the 4 mg versus 3 mg, they're going to be going down, meaning A is going up. So when we create the F equals ma for A, because A is going up, T is its forward force, making the 3 mg the resistive force. So the resultant force that comes from that difference is going to be the mass of 3m times some acceleration that we don't know. As for B, because it's going down, the 4 mg is its forward force, and now I take away the tension to give us 4 ma. A's expression we can rearrange to get T on its own, so T equals 3 ma plus 3 mg. So then, for this, we'd have 4 mg minus the 3 ma minus the 3 mg, because it's all being minused, equals 4 ma. Thus, 4 mg minus 3 mg is just a singular mg. Add that over here, you end up with 7 ma. Therefore, the m's are going to cancel, and a is left being g over 7. So that's your initial acceleration. But as for the tension, if we now plug that back in here simply, T equals 3m times by the g over 7 plus 3 mg. So together, if you were to just bring the mg's together, that would leave you factorized out 3/7 plus 3, essentially, mg, which together is going to be 24 over 7 mg. Now that you have this acceleration and tension, we're now going to want the speed of A when it's 0.7 meters above its starting position. For this, we are going to need some Suvat equations. So we'll have our S, U, V, A, T. The S is 0.7 because it has risen 0.7 meters. It's released from rest, so U is 0. V is what we're trying to find. And the acceleration we just had as G over 7. So we don't need to worry about time here. Instead, we can go straight to saying that V from our V squared equals U squared plus 2AS, like with the previous question, is going to be the square root of now 0 squared, which will still be 0, so it makes no difference. So we can focus instead on just the 2AS, the 2 times G over 7 times by the 0.7, which together could get you the square root of G over 5. Now that we have this speed, we can then say we'll find the acceleration of A after C separates. So once C has separated, once C is completely gone, we're now only going to have a weight on the right-hand side of 2 mg. This now means that the left-hand side is heavier than the right-hand side. So A is now going to be what's travelling downwards, well, accelerating downwards predominantly, and B is going to be accelerating upwards. That being said, the reason for my hesitation just then is that A is still travelling upwards to begin with. It's just you're accelerating in the opposite direction. As I've said before, you can't start now moving downwards until you have first of all come to a complete stop. For this, we're going to have a new acceleration downwards. So for this, we'll need more A expressions and B expressions. Unlike last time, A is not now just going to be accelerating downwards with gravity, because there is still some weight from B pulling it back upwards via tension. So A here, now because it's moving downwards, the weight is now the forward force, so 3 mg minus T equals 3 ma. And for B, because it's moving up, that's now T minus 2 mg equaling 2 ma. So from the top, we can get that T is going to equal 3mg minus 3ma. So 3mg minus 3ma minus 2mg equals 2ma. Bringing the like terms together, 3mg minus 2mg is just a singular mg. Add the 3ma on the other side to give you equal 5ma. M's cancel, and you're left with the acceleration just being g over 5. Now that we have the new acceleration, now we can start making our suvats once more. We're after the greatest height, so we're looking for how much it's going to go up. So you're after your S. The U that A is going to have is the V from the first stage, because the speed it has before the situation changes has to be the same speed as when the new situation starts, because you can't just suddenly change speed in no time. So that, yeah, is going to be your root of g over 5. The V, because it's the greatest height, is going to be 0, because if it had still a velocity then, it would either be going up still or going down already. And then your A is going to be the negative of this here, so minus g over 5, because your acceleration is in the opposite direction to your velocity. Once again, we can use the v squared equals u squared plus 2as, but we're going to have to rearrange to get s on its own. So it will be v squared minus u squared over 2a. So v squared is just going to be 0 minus u squared, we'll just get rid of the square root, leaving you with g over 5, over and 2 times the minus g over 5. So to start simplifying, first of all, the 0 here basically is making a difference, so it might as well just be minus g over 5 over 2 times minus g over 5. The minus g over 5s will cancel with each other, just leaving you with a 1 on the top, and so you are left with a half, or 0.5 meters, once C has separated. But again, just to bear in mind, it's the greatest height above its starting position. A had already risen 0.7 meters before C separated. So the greatest height above its start is actually 0.7, add the 0.5 to give you a total of 1.2 meters. Okay. If we were good with that as well, and we can see how we have managed to apply these concepts to each part of the question to find each of the requisite pieces of information, let's just round off by looking at one further question. This time we're turning to that other model of pulley that I mentioned before, wherein one particle is actually on a horizontal surface, and it's just the other one is descending down. So two particles A and B have masses of 2m and 3m respectively. The particles are attached to the ends of a light inextensible string. So because it's inextensible, the acceleration is going to be the same for everything. Because it's light, we don't have to worry about the mass of the string. Particle A is held at rest on a smooth horizontal table. So smooth, there's no friction, there won't be an AS. The string passes over a smooth pulley, telling you that the tension is the same throughout, which is fixed on the edge of the table. Particle B hangs at rest vertically below the pulley with the string taut, as shown in figure 2. Particle A is released from rest, assuming that A has not reached the pulley, which would mean that B would have to suddenly stop midair. Find the acceleration of B, the tension in the string, and the magnitude and direction of the force exerted on the pulley by the string. So, first of all, the acceleration of B, we're going to need to create our F equals ma equations. So, as always, we're going to have a weight here coming down, so that's going to be 3mg. Here, while there technically is a weight going down of 2mg, because we're just going to be working in the horizontal and it's a smooth surface, that's not going to make a difference. What does make a difference, though, is that there's tension coming up in the string and then tension going to the right. Hence why A moves to the right, and hence why there's a resistance to B here. So for your equation of A, we can simply say that the only resultant force that matters is going to be T. There's no resistance. So T equals 2ma. And then for B, because it is moving downwards, the 3mg is going to be the resultant, or the forward, sorry, minus the T to give the resultant, leaving you with 3ma. We can, of course, now just substitute this T in here. So 3mg minus 2ma equals 3ma. So 3mg equals 5ma. The m's cancel, and you can get that A is 3g over 5, or 3/5 of g. Once you have that acceleration, you can then just put that into the tension for the string. So again, the tension equals 2ma. So T will equal 2m times by that acceleration of 3g over 5, giving you 6 over 5 mg, newtons if you want. So then as for the magnitude and direction of the force exerted on the pulley, this again was something I was just speaking about before. What we're going to do is we're going to zoom in on the pulley here. Whereas you've got your line coming this way, line coming this way. The tension, just as how the tension is going to the right for A, it's also going to the left for the pulley, because tension is acting in every direction simultaneously. It just depends on the thing that we're looking at, which direction is most important. Again, T will then be going down, it's pulling down on the pulley. What we're now going to do is we're going to, just for simplicity's sake in terms of our diagram, ignore the fact that this was a circular pulley and draw this instead just as a right angle here. And what we can say is that the resultant is going to be a force or a diagonal that splits it right down the middle, because these tensions are the same as each other. So this angle here, therefore, is going to be 45 if we split the 90 in half. When it says so that what is the direction of the force, you can say it is like 45 degrees below the horizontal or 45 degrees to the left of the vertical. It's mainly the magnitude that we have to worry about. As I said before, this resultant here is like the sum of the two components of these right-angled triangles, where the T here, the tension, has to be the hypotenuse because it is the resultant. Everything else is just a component of this. So looking in isolation at one of the right-angled triangles, we can say that the side we're trying to find here is the adjacent, and this is the hypotenuse. So adjacent and hypotenuse will be cos 45 equals the adjacent we're trying to find over our hypotenuse of the tension, and we know that the tension actually is the 6 over 5 mg. So times that up, 6 over 5 mg cos 45 equals to A, which we can simplify slightly because we should know that, or we can work out that cos 45 is going to be root 2 over 2. So we end up with 3 root 2 over 5 mg. But then, as I say, because we've got two triangles, and it just so happens that their adjacents are overlapping with each other, we should technically times this by 2 to get R. So R will be 2 times the 3 root 2 over 5 mg, making it 6 root 2 over 5 mg newtons that the pulley is essentially experiencing as it is pulled left and downwards simultaneously.